So for the last talk, before we go for another coffee break, I will not talk around the bush and Halvar Flake.
Thank you. Well, good afternoon. I'm happy so many of you came here. I'm going to talk about a rather obscure topic, and unfortunately, I'm not going to show anything new. I'm mostly going to talk about things that I have found useful, but that were never available in quite the form that I needed them. Specifically, I'll talk about heap visualization tools and things that I would want to have that nobody has built yet. So it is 2012, and looking back at the last 10 years or so, we have made a lot of progress in security. Realistically, heap metadata attacks are essentially dead, except in very rare circumstances. ASLR and DEP are no longer the new normal, they are normal, meaning every modern operating system has them, and unless the application vendor screws up badly, whatever application you're attacking can more or less be relied upon to have a fully randomized address space. Which means that if you want to compromise a machine, you are relying on having an information leak to break ASLR, or you're relying on something else, and you're oftentimes going to be relying on fairly complicated and application-specific conditions, which you'll have to manipulate in a complicated way. Which means you will be programming what I call a weird machine. So what is a weird machine? If you think about it, an application, in the way that it runs, defines a machine, a state machine, and normal interaction with the application means you transition the state machine from one transition to the next, or from one state to the next. Say, you issue a hello command to an SMTP server, well, that transitions its state. So the interesting thing is that once the attacker corrupts memory, this machine enters a weird state, a state that should have never been there. All the transitions are still intact, so the next time the attacker sends data, the transition will operate on corrupted data on a weird state and transform this weird machine into an even weirder machine. So what happens then is that the space of possible states explodes, and the attacker can essentially drive this weird machine to the most absurd state possible, which normally for the attacker means executing code chosen by the attacker. So exploiting stuff is setting up, initializing, and then programming the weird machines that arise through memory corruptions. So the weirdness or the difficulty about programming weird machines is that they are, first of all, application dependent, meaning, well, because the transitions are defined by the application logic and the implementation of that application logic, of course, everything that I can do, every instruction, is dependent on that application. Secondly, they're dependent on initial state. If I'm corrupting the heap, for example, what happens to my program thereafter very much depends on the initial heap layout. This leads to the next problem. These things are super difficult to control. Well, the attacker needs to spend a lot of time setting up a known initial state or a vaguely known initial state so that the application doesn't crash the next time he interacts with it. I mean, a nice example for this is any modern Windows operating system. If I corrupt heap metadata and then perform a bad heap operation on that metadata, the application will exit because the application detects the heap has been corrupted. So I need to make sure that such things don't happen. And even if I try to do everything right as an attacker, normally there's probabilistic risk of the machine just blowing up under my feet. And this is this arises from the fact that you have unknown initial heap state because this heap has memory. The heap is history dependent if you want. And you never know what state the heap was in when you started attacking the machine. Or usually you don't know. Secondly, if you have a multi-threaded environment and a multi-core system, you have built-in non-deterministic heap patterns, or meaning one thread gets preempted, the other thread starts operating on the heap, and just gets all really messy. So in order to make the attack manageable for the attacker needs to have very, very fine-grained control over the heap. And then once he achieves this, he can start building information leaks. And a few nice examples of this. There's a way to build an information leak once you can overflow with an ASCII string out of an existing buffer. And you have a Unicode string that you can read out. This is the case in most browsers because your JavaScript strings are going to be Unicode. And if you have any ASCII string, then the trick to leaking memory into your JavaScript interpreter, or leaking information from memory back into your JavaScript interpreter, is that you make sure that you overflow with your regular ASCII string, which is terminated by a single null byte, into an existing Unicode string, which is terminated by 2 null bytes. So what you do then is you override the 2 null bytes with the last character of your ASCII string and the null byte that terminates the ASCII string. So now you have unterminated the Unicode string. If somebody tries to read the Unicode string now, he'll get a whole bunch of random data from behind it and discloses pointers and so forth and so forth. So this is a nice example how you can take a regular overflow and build an information leak out of it. Another popular trick, which happens to be folklore, which means you'll see it in random exports, but nobody seems to talk about it, is summoning of a vtable pointer into a free block. What this means is I have an allocated block, and I've got a free heap block, and I overflow into the free heap block. And then I ask the application, please generate a new object into that free heap block. Application calls operator new on an object and puts a vtable pointer into the middle of the string that I've used for overflowing. So if I read that string out again, I now get a vtable pointer of an object echoed back, and the vtable pointer tells me where the base address of the module is where this object originated from. Now these are just 2 examples. There's literally millions of them because we're speaking about somebody programming this corrupted weird machine in a way that it gives you back the information that you want. Okay, so controlling and programming the heap layout is absolutely central for building exploits these days. It's the central problem, really. That's why it gets its own slide. Okay, now the thing is that, well, we need development tools for programming the weird machine, because exploitation is weird machine programming. Weird machine programming is really hard. I mean, programming is hard already. We see that every day when things crash. Programming a probabilistic undocumented CPU with weird instructions is that much harder. And we really don't have decent development tools at all. We're seriously under-tooled. Every time, I mean, realistically, at the moment, attackers are solving this by burning themselves out or burning themselves through the enthusiasm of their youth. So you spend 6 months on getting something to run, and instead of trying to make things smarter, you're just bashing your head against the problem until it eventually works. It's, I like to compare this to digging trenches with chopsticks. So there's many ideas on how you can build development environments for weird machine programming. The trouble is that most of them are either infeasible or at the border of what is possible in computer science. So what I'll restrict myself to here is let's just focus on something that we know how to build and that just requires engineering and no thought, if you want. So I'll talk about what I want from a good heap visualization tool. And the only thing that would be required for building such a thing would be engineering. There would be very little research required. So the thing that I'm coming back to is a tool called HeapDraw. Gerardo Richarte from CoreSDI built the first visualizer that I know of. And I vaguely remember having seen a prototype as early as 2004. And then he publicly demonstrated it at some South American conference in Mexico, I think, in 2006. And then in 2007 at STIC in France. And up to this day, it's still a fantastic idea. I don't think I could have possibly finished any decent heap exploit in recent years without having had something like this. And the idea behind this is this is, by the way, a slide directly stolen from his 2006 presentation. You start drawing the heap as a bunch of rectangles. And on the y-axis, you've got your address space. And on the x-axis, you have time. And when a block is allocated, well, you draw it, and when it's freed, it ends. And it's really as simple as this. And what you get from such a tool is you get a very, very direct and intuitive understanding of what is happening on my heap right now. So Gera's tool back then consisted of 2 components. There was some data collection via setting debug breakpoints on RTL allocate, heap, and free. There was some ltrace and LD preload stuff on Linux. And then there was an IDA plugin that visualized the results with OpenGL. And an attempt at rewriting it in Python, which didn't scale. We'll get to the scaling of this later on. It was an awesome tool, Sketch, in the sense that was good enough to be used in 1 or 2 situations, and was good enough to get the idea home, but it wasn't a tool in the sense that you can just give it to somebody and it'll work, right? And the amusing thing about HeapDraw is that almost everybody that I know that writes heap exploits has built himself a ghetto version of the same tool again. So by now I've seen, I think, 4 or 5 different re-implementations of the same tool. All of them are crap, and all of them have just been built to get a job done, and nobody has ever sat down to re-engineer this into a proper thing. So we did the same. For our training classes for teaching heap exploitation, we built a crap remake of the of Gera's tool. It's super messy and was just there to get the job done. And it's also very similar in its architecture. It's a DLL injection-based data collection and then Java and OpenGL visualization. And right, so perhaps I'll briefly show it. This is what it looks like then. We'll play around with this a little bit more later on. We see all these green blocks or green things here, and we can already see the performance problems, especially on a laptop without a fast graphics card. And then we can see when we zoom in, oh, there's quite a bit of heap activity here. Black blocks here are blocks that have been allocated and have been freed again, whereas green blocks are still alive at the time of this tool loading the dump. And yeah, this allows me to skip around the heap, and the heap is big. We'll talk about the actual scale of the heap later on, and it's really slow, especially on a laptop. It's not this bad on a workstation, but it's still pretty bad. Okay, so what I'll talk about now is if I was to get somebody to re-implement this, what would need to be done, or what things would need to be kept in mind when you re-implement this. And there's a whole bunch of things to keep in mind. First of all, you've got pretty ridiculous zooming requirements. A large block of memory can easily be 360, 400 megabytes big, or even more. And you need to be able to zoom between very large blocks and very small blocks, because something as small as 4 bytes will become important to you. So you need to have a zooming between 500 million and 4. As a comparison, Earth is about 12 million meters in diameter. So the zoom level is the equivalent of going from 30 times the size of Earth down to 4 meters. Yeah, well, Google Earth, anybody? I don't know. It's you need to zoom a lot, and it creates performance issues. The other thing that you need to be aware of is gap skipping. This means that your address space is usually quite sparse. You've got a bunch of megabytes or a couple hundred megabytes where all the heap activity is, and then you've got, I mean, we see this here. We've got activity here, and then we've got a huge gap in the middle, and then we've got more activity up here. And this gets worse on 64 bits and in a situation where you've got more heap activity, where you'll have half a gigabyte of nothing, and then stuff again. And you need to somehow have your UI display, okay, ... here's nothing, and then it starts again somewhere else. The next thing that's surprisingly important is arbitrary and independent scaling of your X and Y axis. Our visualization is millions of bytes high, and in any decent, or not decent, in any realistic program, it's going to be millions of events wide. And oftentimes, well, we saw this here, right? I can zoom into stuff again. And, wait, let me zoom out again. We had this, these very, very brief blocks that were allocated somewhere. Right. So you see that I've got very narrow blocks sometimes, and I need to be able to, well, understand what's going on in these narrow blocks and be able to put a sequence visually on what happens where, even when they've only been allocated for a very brief period of time. At the same time, I've got blocks that have been around for a long while, and you can see how I'm squashing and stretching the visualization all the time. So independent scaling of X and Y axis. Other things that you really, really want. Meta information on click. You want to be able to click on a block, and the tool should be able to tell you, hey, this block is size blah. It was allocated here, and these are the other things I know. Now, in an ideal world, you would even get a stack trace for its allocation. We'll get to the reason why we can't actually do this later on, because there's performance issues that we really need to be careful with. We want to have the UI give us the capability to search and highlight based on criteria. We want to be able to say, hey, can you give me everything that was allocated at this address? Please find me these blocks. Can you give me everything that has a particular size? Please find me this. Can you give me anything that was allocated after this other block was allocated and is of a particular size, and so forth. Now, something that would also be awesome is coloring by type. Let's assume for a second that if you collect a block, or you free a block, you write the first double word of that block along with all the other data to the file, which gives you the vtable pointer of what was just freed, which retroactively gives you essentially the type of the individual blocks. So if you have Microsoft debugging symbols, you would essentially have the ability to say, now give me everything in this heap, or highlight me everything in this heap that happens to be a DOM element. Very nice. And then we want horizontal and vertical helper lines. You see these red lines here everywhere? They're for events. So you interact with an application, you want to be able to say, okay, if I load cnn.com in my browser now, this is the red line when I click the load button, and this is the red line when the page is loaded. So you can see through interaction what happens on the heap when you do something. The same thing you want the same thing horizontally as well, because let's say you find a crash because your use after free exploit isn't working properly and you're dereferencing memory that isn't there. You want to be able to put a horizontal line in it and then trace back to see what blocks were allocated previously at this address. And now speed. Speed is really an issue, and I've got no good solution for this yet. You've seen how slow it is on this laptop. It gets marginally better with a fast graphics card, but it's not perfect. And I recently had the displeasure of working with a popular antivirus product for a couple of days and trying to make sense of what it was doing on the heap. And that thing was doing about 30,000 heap operations a second in the background. So like within a couple of seconds of running the machine with the AV in the background, I had a gigabyte big heap logging file and millions and millions of heap events. And at that point, this solution of drawing OpenGL rectangles and just leaving it to the graphics card to scale it or to zoom it doesn't really work that well. Another problem I'm running into a lot is in this prototype, I'm using, the OpenGL doubles as coordinates for the rectangles directly, and the address space is bigger than the precision of the doubles. So sometimes you'll get blocks jump around because of floating point rounding problems. So bad idea. This actually, if somebody knows a game programmer, this would be a problem to discuss with him. It's possible that some form of ray casting where you essentially send a ray into your abstract model of the heap and see whether it hits a block might work pretty well. Right, now I've talked a lot about what the problems in the UI are, and there's lots of more problems in the data collection. Now, one of the biggest problems with data collection on heap is you have to minimize thread skew. Now, what do I mean with minimizing thread skew? We want to debug exploits that we want to be able to use outside of our laboratory, right? We want to build something that is actually capable of compromising a machine. Now, the trouble with this is that multi-threaded heap layout is extremely timing dependent, meaning if I change the timing of the threads drastically, I get a very different heap layout, which might mean, well, you essentially run into a Heisenberg problem, right? You want to measure something, but you are not allowed to actually influence it. So you run into the problem that in an ideal world, you would want to have zero impact of the presence of your tool on heap layout, and practice that is not achievable. Just plain and simple, it's not possible. Because your tool is bound to eat up some cycles moving data from A to B. But what we absolutely need to do is we need to minimize timing skew when we're dealing with multi-thread applications, which means if we want to make this useful for our browser, we need to have the minimum timing skew possible. And this need for speed dictates a lot of the other design decisions, because it also tells us that we can't do a lot of things that, like, it tells us you can't have these nice things, because if you have these nice things, you'll get nice things for a heap that will never occur in practice. So things that we can't do. We can't use debugging. This was the main reason why the initial, Gera's initial prototype needed to be rewritten for us, was they collected data using debug breakpoints and so forth. And that's super heavy. That's a context switch per allocation. first of all, your application is no longer usable, but secondly, the layout of the heap has very little resemblance to the layout of the heap in reality. So you need to stay in the same address space to minimize context switches, and you need to buffer data in memory as much as possible while you're collecting it. We'll run into interesting conflicts with this, with the other design goals, by the way. Because what you also want is no heap interaction, meaning you need to inject your tool into the other address space or into the other process, but ideally it shouldn't take up any address space in that process, right? Because if you're doing any form of heap interaction yourself from your tool, like allocating memory, you are now influencing the heap layout. Bad idea. You can't use SDL without writing your own allocators. You cannot call any operating system APIs that allocate memory, which means you can't use Win32 pipes and so forth. So you need to be super minimal, just put stuff into a memory buffer somewhere. We'll get to this problem in a bit, and then dump it to disk eventually. Now, the next problem you're running into is minimal address space interaction. Your tool should ideally not take up address space in the process that you're in. Now, this is, I don't know how to do this, really. Perhaps you can map it into kernel address space, modify paging descriptors to make sure that you can write there and execute there. I don't know. In my situation, I took the dirty hack of just making sure that my tool is mapped at a place that is very unlikely to be mapped for regular heap interactions, which is usually right below the main executable. The reason why the operating system is very hesitant to give out the memory or to use the memory right below the main executable for heap allocations is it can't grow that section, like it can't grow that memory area anywhere meaningful. So, but ideally you want to have as little address space that you take up as possible. The next thing you need to do is exporting data on request, which means, well, I said that we have to buffer in memory, but what good is buffering in memory if I buffer the last 1,000,000 heap events in memory, and then my user interface, I can't see what happened for the last 900,000 allocations. So I need to have a way to send a signal to that process to give me that data. Or perhaps I need to buffer that data in a shared memory section in kernel address space. I don't know. Something like this. The next question is, what data do I need to export? Well, of course, I need to export allocations and frees, the size of the allocation, the address of the allocated block, ideally the address of the caller. Perhaps if you're doing free, the first double word of the free block. But then if you start exporting much more, you run into hard disk space problems because, well, 30 seconds of running a big AV gives you a gigabyte of log. Or you run into timing skew issues. So you have to be really careful about how much data you take and how much data you export. The next thing, heaps in heaps. Now, in reality, very few applications use the operating system heap straight away. Application-specific heaps or application-specific heap caching and so forth is really common. So what you oftentimes see is you see an application allocate larger blocks using the operating system allocator, and then have the application-specific heap implementation allocate smaller blocks within these larger blocks. And in essence, we want to have a data collector whom we can tell, okay, in this module, at this address, there's the application internal malloc. In this module, at this address, there's the application internal free. And register EAX here, upon entry to alloc, contains the size of the allocation, and so forth. And this gets a little bit messy because you essentially need to have some sort of description language where you can tell the data collector, this is how it works. I haven't really found a nice and pretty solution to this either. But that stuff would be really useful or important, right? Because let's say I want to use the heap logging, for example, on, let's say, Internet Explorer. Internet Explorer uses some weird caching scheme where they, well, apparently allocate memory from the operating system in large chunks and then dish it out and cache it and garbage collect it and do something weird. If I can't easily adapt my data collector to collect data in Internet Explorer, it's not that useful. This is an example of a heap in a heap. Now this is a memory dump from, or a memory trace from Adobe Reader. And what you can see out here, like the big green block, is an allocation that Adobe Reader did from the operating system. So it called malloc, like Visual Studio malloc or whatever, to allocate a larger block. And then Adobe has an internal heap called the bib heap. And these small blocks that you see here are allocations that have been done by the bib heap inside of the bigger block allocated by the operating system. So, right. The other thing that one would want is the ability to get callbacks on certain events. So the 20th time that you hit a particular point in the program, please issue an extra event. Like put an extra heap event into your logging. The reason for this, again, is to be able to see in the UI later on, okay, this is when I started downloading the file or when I started parsing the file, and this is when I ended parsing the file, and this is what happened in between. Following child processes. This is particularly annoying nowadays in Adobe and Chrome and browsers generally because they spawn child processes all the time for new tabs or for sandboxing and so forth. And there's no elegant solution really to make sure that if you have a data collection DLL in one process and the application spawns another process that you follow this thing around. So same thing, well, on Linux or Unix it's much nicer because LD preload can be done globally, so you preload an SO for every process. So if they fork, your DLL migrates along with it. But well. Oh yeah, cross-platform, cross-operating system. You need a data collector for Windows, Linux, OS X, 32 and 64 bits. Right. Yeah, the last thing that would be useful, but I don't think that anybody's ever going to build this, is extra code that gives you meta information about the operating system heap. So, for example, under Windows, if you free a block, most of the time it'll like be put into some sort of free list, which means, I mean, heaps, almost all heaps operating on a first out, well, last out, first in, low fee paradigm, right? The last block that you free is the first block that you're going to get back. So it would be really nice to be able to see the blocks that would be put into free lists or that are put in free lists and have them highlighted. But I don't think anybody will ever do this because it requires taking apart the heap implementation and then writing a lot of operating system specific heap code for it. I'm not even sure whether the effort for doing this would be justified. So after all this talk, what I'm going to do is I'm going to show a little bit what, like how this would be used in practice. We're going to do, and how one would get insights about what happens on the heap through this. So what we're going to do is we're going to look at a simple PDF file that uses JavaScript to spam stuff on the heap, and that then frees stuff on the heap again. And then we're going to look at what happens there. We're going to compare what happens under Windows XP, which does not use the low fragmentation heap, and what happens under Windows 7. So I'll launch Adobe. Yeah. Okay, Adobe has been launched. Now we tell the heap UI, this is my heap now after Adobe has been launched and nothing has been loaded yet. Okay. Now I load a file. The file gets loaded. And JavaScript starts executing and gives me an alert box, I'm about to do something. So I look at my heap again. I reload the input file, ignore this dialog, and ignore the focus issues. Okay, so the red line here was the point where we reloaded the old file. So everything that happened before was before we started loading the file. Everything that happened thereafter is stuff that happened after we started loading the file. Right now the file is hanging on the message box. So well, it tells me it's about to start spamming 2,000 blocks of size 2,000 onto my heap. I tell it, go ahead. It tells me it's done putting data on my heap. So I have a look. Focus issues. Okay. VMware. Okay. So No file loaded, we click OK. Then we see here memory being allocated, and up on the top right we also see memory being allocated. And this is the stuff that we just spammed onto the heap. And let me zoom in much further. Right, so these are the blocks that we've just created. And they are of size 176C, which is a little bit more than, well, which is essentially what you get if you spam a 2000 character JavaScript string, or no, 2000 byte character string to the heap. And we've got many of these. Right, okay. Now, create a few more blocks on the heap. And let's see what happens then. Yeah. Sorry for the confusion. Perhaps I should just minimize this for a sec. Okay, so file open. First time we click the button, first 2000 blocks put on the heap, 2000 more blocks put on the heap with a different size. So we see how spraying stuff onto the heap is growing stuff. And now let's try to see whether we can selectively freeze some of it. So what we're going to do now is, in the JavaScript code, we're going, what we've done so far is we've created these strings and kept a reference to each one of these strings. And we've kept them in a JavaScript array. So what I'll do now is I'll go through the JavaScript array, and every second element of the array I'll delete. Like, I'll just erase the reference, and then when the garbage collector kicks in, it should let go of every second block and they should be freed again. So I've done this. I reload and fight with the focus issues. Okay. All right. Now we see here that a bunch of blocks that used to be green have turned black. Like these blocks here that we've allocated on the first round of spraying have turned black. And if we zoom in more, we can very, very clearly see that every second block here was released and freed. So yay, we now have every second block free. And we've created gaps on the heap of a particular size. And this, of course, is then useful for arranging the heap layout in the way that we need to arrange it. Okay, let me see for a second. I'll zoom in a little bit more. Something that is interesting here, by the way, is, and this is a nice example of why heap exploitation can be annoying. We see here that every couple of allocations that we perform, somebody, not us, performs an individual allocation that is slightly larger than what we are allocating. And then when that block gets freed, it gets put into a free list somewhere. And then we allocate the next block that we allocate from that free list. And the block is cut off, like cut in the middle, essentially. And the small block goes into another free list. But what this means is that the next allocation thereafter isn't sequential. Right? So what we see here is that, okay, sequential allocation, sequential allocation, sequential allocation. And then sequential allocation, weird allocation that we don't know where it's coming from, freeing of that allocation, cutting off the block, our allocation. Now, this is really annoying if you as an attacker rely on exact placement of objects later on for your overflow. And this also explains why so many exploits in the wild have a probabilistic failure rate of a couple %, right? Because stuff like this can happen. The heap layout can be shifted a little bit, and then you're confused and you don't quite know why. And having a tool like this is really helpful for debugging unreliability in such exploits and just seeing what's going on. So perhaps what we should do now is let's have a look at the same thing in Windows 7. Well, actually, I'll have the garbage collection go through and release all our strings, and then we'll have a look at what the heap looks like once we're done. And then we'll look at Windows 7. Come on, piece of crap. Here we go. All right. Now we see